Hello.
Hello.
We're gonna do a quick screencast um, for looking at different kinds of graphs for enzymes. All right, let me power up the old iPad. Come on. Oh my goodness, I've got a lot of things open. All right, so this is not that I want to go. I want to go to this. All right, so I've posted this online now, and it's just many different graphs, and it just will get you some practice. If you can fully understand each of these graphs, you should be in pretty good shape. So for the first one here, we are looking again at substrate concentration on the x-axis and reaction rate. And we see that there's a maximum reaction rate, all right? And if we're dealing with substrate concentration, that means that that is the substrate point of saturation, right? And that what that also means is that we have some limited or constant amount of enzyme added in this reaction. And the way that we do any of these curves is that we have many different reactions happening. So for example, I have some amount of enzyme and a little bit of substrate, and I get that reaction rate, right? Then I have another tube with some amount of enzyme and more substrate, and I get that, and so on. So think of each of these as data points that you are collecting, and that should make more sense when we do the lab. All right, the next graph is, that was the effect of substrate concentration. Now we're going to look at determination of the enzyme reaction rate. So here we're looking at the product being formed over time, all right? The product being formed. Anytime you see kind of this situation, we are going to also have a graph that's tapering off, all right? And in this case scenario, actually I'm gonna start over here. In this case scenario, the fastest time, the fastest reaction rate is here when it's linear, all right? And this is where you're always going to measure initial reaction rates. And it's always this linear part right there, all right? And the reason that we are seeing it taper off here is most likely because you ran out of substrate, all right? So you have a whole lot of enzyme, or you have a lot of enzyme in there, but we're running out of substrate. So as you make a lot of product, you have less and less substrate there. Okay, next graph is the effect of a cofactor or a coenzyme, all right? And remember, the difference is that one of them is organic and the other is inorganic, all right? And so the cofactor is inorganic, is that right? Oh God, don't let me forget. Cofactor is inorganic, yes. And the way I always remember that is we know that an enzyme is a protein, so that is going to be organic. The cofactor is inorganic, and that usually means like a heavy metal, magnesium, iron, etc. All right, so here we're just looking at the extent of the reaction, like how much reaction actually happened over time. And without a cofactor, the reaction might work like that. But when you add the cofactor in, you see that the extent of the reaction goes up significantly, right? So both cofactors and coenzymes increase enzyme function and therefore increase reaction rates, all right? Remember that enzymes are proteins, so there's a strong effect of pH and temperature, but here's an example of pH. So if we had to find looking at this graph, the optimal pH for the enzyme pepsin, which is in our stomachs, it's about 1.9 or 2. If we had to look at the enzyme trypsin, which is in our small intestines, its maximum or optimal pH is 8.5, all right? So the peak of this represents the optimal pH for that enzyme. So that means if I took pepsin enzyme and I put it into, I don't know, let's say the small intestines, which has a higher pH, it's not going to function that well because enzymes have an optimal pH. At pHs, remember that changes in pH can have a direct effect on the protein shape, right? So changes in the pH can affect protein shape, and in particular, pH often does that through affecting pH bonds. And we know, sorry, not pH bonds, hydrogen bonds. And we know that those are really important, for example, for the secondary structures, alpha helices and beta pleated sheets, and also for tertiary and quaternary structures too. All right, the next two have to do with inhibitors. So here we're talking about what would happen with a competitive inhibitor. And remember, a competitive inhibitor means that it competes for the active site, right? So here's the actual substrate, and here's the inhibitor, right? So this is the inhibitor, this is the normal substrate. This is a competitive inhibitor. They both bind the active site. So without an inhibitor, we're again looking at substrate concentration. So up here would be the point of saturation. So without an inhibitor, you get this same kind of curve. If you, with an inhibitor, it is dramatically affected at lower substrate concentrations, but as you increase the amount of substrate, you can out-compete the inhibitor. So you can get back up, you can get to full reaction rate and get to full reaction rate with a competitive inhibitor if you add enough substrate to outcompete it, right? So more substrate added, more likely to out-compete the competitive inhibitor. All right. Here we have effects of a non-competitive inhibitor. All right. So remember, I'll just draw my little drawing again. All right. So here we have the blue dot here is the non-competitive inhibitor. It binds to a site that is allosteric or away from the active site. So if it's not bound, the substrate can bind the active site, no problem. If that competitive inhibitor is bound to the allosteric site, then our substrate cannot get in, right? It cannot get in because the active site has changed shape. And because of that, it doesn't matter how much substrate you add here on the x-axis. It doesn't matter how much you have. You're still just going to have a bad enzyme. So a non-competitive inhibitor causes a bad enzyme, right? So a non-competitive inhibitor just makes a bad enzyme. The active site is screwed up and it just doesn't work as well. All right. Next one is effect of temperature. So here we have the reaction rate versus temperature. And remember that all proteins do have an ideal temperature, all right? But I will say for the majority of enzymes in our bodies, which is about 37 degrees Celsius, the majority of enzymes in our bodies have an optimal temperature that is around 37. Here, the graph is shown maybe a little bit more, like 40. However, high temperatures as we know, can cause denaturation and denaturation. I'm just going to put denaturation. So instead of going from our nice little enzyme that has an active site in its three-dimensional form, denaturation causes it to go back to its primary structure, and therefore you do not have an enzyme that can function. All right. And then the last one here, which I'm not too worried about, but I'm just going to go over it briefly, is that this is talking about how the shape of an enzyme is affected by temperature. So here we have the enzyme shape. It seems pretty good up until a point. And again, at high temp, you get a loss of enzyme shape due to denaturation, and therefore it tumbles down. And any enzyme catalyst reaction will also tumble down. All right? So I just wanted to go over this worksheet that I posted so that everybody is clear on that. All right, come to office hours if you have questions. Chip, chip, cheerio. Bye.